Hi, welcome to the next video on LabVIEW. So in this video, I'll be showing the modulation of a double sideband suppressed carrier. So we'll just go to the LabVIEW block diagram panel. So I have already taken a signal, message signal and a carrier signal. So message signal amplitude and carrier frequency. Carrier amplitude and carrier frequency are given through the knobs. And so DSBSC modulation is just with the message signal being multiplied by the carrier signal. So a multiplier block has been taken and it has been already connected to the message signal. One of the input to the message signal and the other input is to the carrier signal. The message signal waveform will be shown on the scope, which is a message signal, and the carrier signal once again on the scope. Similarly, the modulated signal will also be seen on the scope. So now we shall move on to the front panel. So I have got a message signal amplitude which is, let me give, of 2 volts. Message frequency, let me take it around 2000 hertz. Carrier amplitude also, let it be around 3 volts, and the carrier frequency, let it go up to 20 kilohertz. So since the carrier frequency should be greater than the message frequency, I have taken it as 10 times greater than that of the message frequency. Let me run this simulation. Yeah, so message signal waveform, similarly the carrier signal waveform is on the scope. So coming with the modulated signal waveform, you could see that so we have phase shifts on every 0 crossings of our message signal. So I'll just expand a bit and show you. Stop the simulation, expand the waveform graph, expand the waveform graph. So you could clearly see the phase shifts over here. So which will be like M on M and the W format. So you could just reduce the scale. You can just reduce the scale and have a look into more clearly to that. And I'm just reducing the scale. Yeah, so you could see this phase shift. So let me go up, check out the one more phase shift. Yeah, so you have phase shifts for every 0 crossings of your message signal. So if I just take a reference as 50 millisecond as the time instant at which the message amplitude is 0. At 50 milliseconds, yes, we have got a phase shift at 50 milliseconds of the modulated signal. Now, if we want to look into the spectrum of a message signal as well as the modulated signal, to have a look into the spectrum, so right click on the block diagram panel, go to Express, in that go to Signal Analysis and select the spectral block. Place it over here. Yeah. So as soon as you open that block, so you will have the magnitude versus frequency plot. You can have magnitude versus frequency plot, amplitude versus time plot, which we have seen previously with the waveform. So now I'm more Now I'm more interested with the amplitude part or amplitude plot or with the magnitude plot. Magnitude, which will be an RMS amplitude. So that is peak voltage divided by √2. RMS plot, which will be in a linear scale. So once again, magnitude, the peak amplitude itself will be considered, so which will be once again the linear scale. So I'll just select the magnitude plot with a linear scale. power spectrum and the power spectral density we'll be looking at in the coming videos. So coming up this windowing technique, so by default a Hanning window is being selected. So regarding this windowing technique you will be studying in your higher semesters. Need not to worry right now over here. So to plot the spectrum or to take the FFT of any message or the carrier signal, a spectral block is being introduced where magnitude linear plot is being considered to that. So I'll just click on OK. Coming up with the input to this FFT block, a signal. Let me go give the message signal as one of the input. Similarly, I'll take up 3 more spectral blocks to go plot the modulated spectrum as well as the carrier spectrum. Yeah, we shall continue further. So I have taken the spectral measurement of the message signal, modulated signal, and even the carrier signal, whose magnitude will be plotted in the graph. Let me go to the front panel. Yeah, so front panel, I have taken the 3 graphs once again. So let me run this. Yeah, just before running it, let me change the axis over here. Yeah, frequency versus amplitude. Frequency versus amplitude for all the 3 plots. Change the scale. So since the message frequency is in terms of 2000 Hertz, let me change it for 4000 Hertz. Yes, you could see the plot over here, an impulse function exactly at frequency 2000. Since the carrier is of 20 kilohertz, so let me change it to around 40 kilohertz. Coming up with the spectrum of the modulated signal, so I will just change the axis to 40 kilohertz. Yes. Yeah. Continuously run this continuously. Now you could see the message spectrum at frequency 2000 Hertz. So if I just vary the frequency of your message signal, yes, even the plot varies. That is, the impulse functions varies according to the given frequency. Similarly, the carrier signal, I just vary the frequency of the carrier signal now. Yeah, you could see the variations with the frequency of the carrier signal. So now coming up with the spectrum of the modulated signal. So as I vary the carrier frequency, you could see that the 2 sidebands which are centered around the carrier frequency. The carrier frequency now it is to be 23 kilohertz. So centered around 23 kilohertz, the upper sideband and the lower sideband, where the upper sideband frequency is carrier frequency plus the message frequency. The lower sideband frequency is carrier frequency minus the message frequency. Yes, I just increase the message frequency. You could see that. Yes, you could see that both the sidebands are being moving apart. If I reduce the carrier frequency, the message frequency, you could see that both the upper sideband and the lower sidebands are coming very close to each other. So similar thing happens if I vary the carrier frequency, where the upper sidebands and the lower sidebands are being centered around the carrier frequency. Just vary this message frequency, reduce the message frequency, you could see they are coming close to each other. If I increase it, since plus and the minus value changes, that is Fc plus Fc plus Fm, Fc minus Fm, the values changes, they are moving apart from each other. So this is with the modulated signal and the spectrum of the modulated signal coming with DSBSC modulation. Coming over here, so we could see only the spectrum only on the positive frequency axis. Negative frequency axis is not available to going up with this F50 block. Once again, move on to the front panel. Observe the variations with the amplitude with the spectrum also, and just reduce the amplitude of the message signal. Yeah, even the amplitude plot over here is being reduced. Similarly, reduce the amplitude of the carrier signal. Yes, similarly, you could see that the amplitude portion of the carrier signal is also being reduced. So coming up with one more parameter which we had looked previously with the F50 block. So that is with RMS value. So RMS value, now instead of going up with the peak value, I'll just go select the RMS plot with respect to frequency, and I'll just click on selected, click on OK. So before running the code, before going and running the code, have a look into the magnitude or the amplitude over here, which is around 1.6 with the carrier signal, and with the message signal it is around 1.2. So you could see the variations between the peak value and the RMS value now. So I'll just run it. Yeah, previously which was plotted with respect to peak, so it is now with RMS value. So peak value was around 1.2 or 1.16, whereas the RMS value is with 0.8. Similarly, you can change the peak plot with respect to the RMS plot coming up with the carrier as well as the modulated spectrum also. So this is what we have with this DSBSC modulation. In the next video, we shall consider the addition of two sinusoidal signals along with the multiplication, where we could generate a standard AM signal. So in this, two signals, one message and one carrier being multiplied, we could get a modulated signal. To look into the spectrum, the signal components have to be converted with respect to frequency, which is fast Fourier transforms. So we select the fast Fourier transform block, plot that block with respect to frequency, and observe the spectrum of the message modulated as well as the carrier signal. In the next video, so we shall look into the addition of two signals along with the multiplication operation. Thank you.